Okay, Assalamualaikum. Hi everyone. So today I will show you an example related to the open system, which is a turbine. Okay, so this question is designed for a steam. Alright, so in this case we need to use property tables to solve the problems, but first we need to understand the problems. So here if you look at this example question, the power output of an adiabatic steam turbine is 5 megawatt, and the inlet and exit condition of the steam are as indicated in figure 1. So which this is the figure 1 at the left here. Alright, so the input or inlet properties here given is pressure, temperature, velocity, and also the elevation at this position at the inlet, while the output the parameters given here is P2 pressure, and then it gives you the quality, it gives you also the velocity and also the elevation at this position, while producing 5 megawatt of power. Right, so to solve this problem, highlight the important things here. So we know that the power of an adiabatic, so this is the keyword that we need to pay attention, adiabatic. So this means that your Q net will be equal to 0. Right, so the steam turbine power output is 5 megawatt here, so as given in the figure, and the inlet and exit condition is given also. Alright, so it asks you to determine the delta H, delta KE, and also delta PE here. So what we need to do, alright, you can sketch your problem first. Okay, at the state 1 and also state 2. Right, so since this is what we call as steam, we need to determine the phase for each of the state given. Okay, so here state 1 P1 is equal to 2 megapascal and 400 degrees Celsius. And then also given 50 meter per second as its velocity. While Z1 here, the elevation here is 10 meter from the reference point. Okay, so by using this and looking at these properties, basically we can name the phase here, because there are two intensive properties, which is pressure and also temperature here. So by looking at the property tables, we can name the phase. Okay, meanwhile you can also write your state 2. P2 equal 15 kPa, and then you have here x2 equal to 90%. Then you have also V2 velocity 180 meter per second. Also given here is Z2 6 meter. Alright, so since this already given, the quality of mixture means that we know this is a saturated mixture condition. Okay, so this is very important, so that we can refer to the correct table. So first, since we already know the name of the state 2, so now we need to name the state of the phase for state 1. So we need to look at table A5 and search for 2 MPa and 400 degrees Celsius here. So look at table A5, 2 megapascal, which is equivalent to 2000 kPa. Okay, here, and your temperature just now is 400 degrees Celsius. Meanwhile, this T set is only 212.38. Okay, so in this case you can put here T set equal to 212.38 degrees Celsius. So since T is higher than the T set value, means that this phase is a superheated vapor. Okay, so now in order to solve the problems to find the delta H, Ke and also Pe, we need to use the energy equation, steady flow energy equation for this kind of problems where you need to find the value of Q and also W and also other terms in that kind of equation. So for the open system, we can write like this one: Q dot minus W dot equal to M dot delta H plus delta Ke plus delta Pe. So this is only valid for a single input and also single output, such as on this diagram. So you have only one input and also one output. Alright, so since this is a adiabatic, we can cancel the Q dot here, which is the net heat transfer. So you need to write here as adiabatic as your assumption there. And then other terms here, you cannot neglect it because all of them are included in the equation. So now your terms becomes negative W dot equal M dot delta H plus delta Ke plus delta Pe. Alright, so this negative W dot basically is equal to minus W dot out minus W dot in, which is equal to M dot delta H plus delta Ke plus delta Pe. And then since this is a turbine, so no power input to the turbine. Okay, so the power input only specific for the compressor. Now your equation becomes negative W dot out equal M dot delta H plus delta Ke plus delta Pe. Okay, so now since the equation asks delta we call delta H, Ke and Pe, so we can use delta H, which is equal to H2 minus H1, which is the final enthalpy minus the initial enthalpy. So in order to get this, you need to name each of these properties first, then you can get the value of H1 and also H2. Since we already named the state 1 and also state 2 here, which is state 1 is a superheated while state 2 is saturated mixture. Now in order to name the value of H1, this is based on the superheated table, which is table A6, because this is superheated vapor, while state 2 basically is a mixture. Okay, so we need to refer to table A4 or A5. Alright, so now find H1 through property tables for a value of 2 MPa and 400 degrees Celsius. Look at this 2 MPa and also 400. We look at table A6 because it's superheated vapor. So 2 megapascal here, right, with a temperature of 400. So take your ruler and then mark the position here. So the value here for H, which is on the column here, the third column, H, is 3248.4. Okay, so we mark this value as your initial enthalpy, 3248.4. So I think I want to sort this first based on the modified, right? So 3248.4. So write down here from table A5 hash, sorry, this one is table A6. So H1 equal to 3248.4 kilojoule per kilogram. So this is from table A6. Okay, so for state 2 here, this is a mixture, so we need to refer table A5 or A4. So we look at the pressure here, 15 kPa. Okay, so look at property tables. Table A5, since we refer to the value of a pressure, So now 15 kPa is here. Okay, so this is your 15 kPa, and then mark your value of the enthalpy side here. Okay, so here we have HF as 225.94 and also HD 2598.3. Okay, so we need to use these numbers. Okay, so put your property tables right here. So for a mixture here is a little bit different because we need to use some formula, which is H2 equal HF plus X2 Hg minus H4. So this is equal to, right, 225.94 plus 0.9, since this is 90%. Hg is 2598.3 minus 225.94, or you can just use HFG value. So this is 2372.3. Then you get the answer as so this is equal to 2361 kilojoule per kilogram. Okay, so the delta H here will be equal to H2 minus H1, which is 2361 minus H1 is 3248.4. So this is equal to 3248.4 negative 887.4, and make sure that your unit is in kilojoule per kilogram. Okay, so since this is a small hash, right, so all of this unit, all of this term basically in kilojoule per kilogram. Then if you multiply with m dot, you will get the unit in kilowatt on the left side here. Okay, so now we need to find delta KE. So delta KE basically is equal to the change of the kinetic energy. So this is equal to V2 square minus V1 square over 2000. So since this value, I think already given in the equation. Okay, V2 and also V1. So V2 is 180, V1 is 50. So you will get the value as 14.95 kilojoule per kg. Okay, the last one is change of the delta PE, which is equal to G Z2 minus Z1 over 1000. So this is 9.81. Z2 here is 6 meter. Z1 is 10. So the velocity here is increasing, right? So let's do one. Six minus 10 over 1000. So this is produce a very small number, which is 0.03924 kilojoule per kg. Okay, so mark your answer. Check all of the units that this is correct or not. Okay, so now you can also check here. This is answer given. Second question asks for work done per unit mass of the steam flowing through the turbine. So this is the question here, and this is the answers. Work done per unit mass means that it asks you the value in kilojoule per kg, because the unit for work is kilojoule, and then it asks you per unit mass, so per kilogram. So you must make sure that your answer will be in kilojoule per kilogram, which means that this requires a small w as your answer, not a w dot or big W. Okay, so in order to get a small w, we need to rearrange some of the steady flow energy equation here in to write in another form. Okay, so basically we have three forms, which is kilowatt, we have in kilojoule per kilogram, and also in kilojoule per kilogram. So what you need to do from this w dot, right, negative w dot, which I just used from this equation, equal to m dot delta H KEPE. We can just divide this w dot with m dot to get a small w. So it becomes delta H plus delta KE plus delta PE. So it becomes negative w, and the unit will be in kilojoule per kilogram. Okay. So this is delta H. What is delta H? Delta H is calculated just now. Negative 887.4 plus delta KE is 14.95 plus we have here, sorry, this one is a negative value, right? 6 minus 10, okay, negative 0.03924. Okay, and then we put the answer in kilojoule per kilogram, but this is negative W. Okay. So it becomes negative 872.5 kilojoule per kilogram. So if I want the W in positive, so I need to be this value in positive, it becomes 872.5 kilojoule per kg. Okay, so basically this is your workout. Okay, so I think I missed to put W out here. Okay, this one is correct. This one, yeah, you need to put W out. Okay, the last one is a mass flow rate, 5.73 kg per second. So since the question already give out the number of W dot out, which is equal to 5 megawatt, okay, we need to convert this into 5,000 kilowatt. Okay, since we want to convert this into this value, okay, so we need to maintain the unit in kilo. Alright, so the m dot, which is the mass flow rate, can be calculated by using a simple formula here, which is if you want the small w, this becomes big W over m. So this one is a W dot and also m dot. So I need to have a m dot value. M dot equal to W dot over W. So this one is based on the power output produced. So the upper one here is 5,000 kilowatt, while the denominator here should be in kilojoule per kilogram, 872.5 kilojoule per kg. So what unit that you will get will be in kilogram per second. So this becomes 5.731 kg per second. Okay. So this is a question related to the turbine, and I think all of you can look into this tutorial and understand it better.